Okay, so we have the mode extension, and now I want to look at the soft vectors. So
I'm gonna just skip your last problem, yeah, I was watching this before, but yeah, like I said, I kind of just skipped it. I noticed she talks about Cauchy slice, and I mean, I think she's trying to expound upon sort of. I don't know if it's a real theory or if it's just like consciousness perspective or what she means by um, maybe she's meaning like her superposition in space time. I don't know. But she gets asked a lot of questions here, so I don't know if she. I mean, I don't know about this problem, and I think she was kind of just describing maybe how free energy would really work in a system. But like I said, I watched like the first part a couple days ago.
great. So the next step is just to write out explicitly, I guess, what the soft vectors are for a set of.
So I don't know if she started this, but she does use soft theorems, and she just said soft vectors. So I mean, she has quite an understanding of the theoretical reality. So these days she's using, she says dressing. So I'd like to imagine that she's saying these are approximations in space according to our best calculations, and because she's going to LIGO, she's going to CERN, and so she's saying like we're dressing uh, the material universe. It was getting a little bit confusing, like in her latest video, just because I didn't know if she was talking about string theory or what. So, yeah.
Particles with an additional soft proton inserted, or any gauge field. So in particular, the soft vector is going to be different depending on the theory. Okay. So this is the top part of the triangle that we're just kind of taking as starting point here. And I'm going to write out what these are.
Well, so if she's talking about soft factors. Oh, she's saying soft factors. I thought she was saying soft vectors. Maybe she is saying soft vectors. I don't know. Maybe she's from Boston. And then memories and symmetries. So, you know, approximations. I mean, it's high energy, so trying to be conclusive with, or trying to be as evidential as possible of what that black hole is actually doing. Talking about, uh, these just approximations, and memories are probably would entail just this different theories of why they are predicting the black hole to do what it's doing, and then the symmetries are what they can come up with to sort of, I'd say, present their findings.
So kappa squared is 32 pi g, but it's sometimes it's easy just to keep track of it or set it to 2 when a pi g is 1, so there's different.
And of course, like they'll use calculus formulas to, they just have calculus formulas memorized. So it's just like another language. It's just, there's just a language barrier, but there's, different formulas that they know by heart. So they can just keep going through them and going through them and going through them. And it's like, a lot of these, especially these calculus formulas, they're infinite. I mean, from my understanding, just because and then so you go to like null infinity or whatever they call it, like n, and that's like their best approximation for the calculus. So that, I mean, that'd be like measuring and doing all this stuff. If they were looking at an asteroid, then they'd be getting into statistics and they'd be trying to understand, well, statistically, yeah, like this asteroid is going to do this and going to do that, and based on like they, I mean, they're always combining. They got to always be combining calculus and statistics. So, yeah.
Conventions you might see in the literature on this. Yeah. And then for everybody else, we have something different.
So, I mean, they could go out into space and measure temperature, like calculate temperature, because they'd have to be able to, get every angle of. I mean, I don't know what angular momentum is.
So basically written down these expressions for the soft factors. And what I want to now look at is basically we have here what the mode extension for AZ is, or AZ bar, in terms of these made errors. So when we have a setup.
So, I mean, of course, I mean, this is a whole, I mean, that's like, all that math is like a picture of space for her. And you can imagine that, it's just a description for what they're trying to calculate and evaluate and all that stuff. So it's just not very debunkable because it's like very, high processed and clean.
We're looking at something, say, like a ward identity or whatnot, where we have some out.
I mean, I wouldn't say I'm really trying to debunk her. I'm just trying to get like a better grasp of what the heck is going on. So
Here's some Q plus the rest matrix. A different charge equity in. If we interpret this Q, which involves, say, for instance, if you look at the line, wait, 8 pi GQY is that expression, and use the constraint equations, there's going to be a part like we discussed yesterday where you have the radiative fields and then some matter fields. And so we want to literally kind of think of inserting this mode expansion into the S matrix element and pulling out these soft factors. And
I mean, it's like they have their brainstorming of like, the different equations they can use and all that, and then they have all these just representations of, well, soft factors. So you're going for low calculations. I mean, if you're having like, I don't know if they're all soft factors, but I mean, you couldn't have. I mean, if they, I mean, they're doing the best factors they can. Maybe they're not like, well, it's because like once you understood like how many times a straight line is going to, in effect, like refract in space, then you'd understand like our even like if you could see like if you can imagine how many times that your mirror is going to reflect inside of the telescope, you could quantify the distance of where you're looking, in a sense that, well, like if you knew the distance from the moon and the sun, like if you knew the distance, from the moon and then from the sun, and you could calculate those, and that would give you a estimation of what your distances would be to other systems, and yeah, so it's, I mean, obviously, but all these formulas and calculations and stuff, though, they just can use them like whenever when it's needed, and so it's not like they're just pulling Like, I mean, this is like 400 years, 500, 600 years of uh, science or science and math and stuff like that. But yeah,
And what I'm going to try to show today is that it's a bit of like expectation value interpretation. So these are going to give you, with some differential operators acting on it, just like the radial electric field for a boosted charge. And so it's kind of nice to see that because it connects this picture of where these ward identities are coming from. And then so motivates this notion of how like the memory effect is like the step function compared to an overall shift that's just the pure gauge for these large gauge transformations. So
yeah. So I mean, they are talking. I mean, they're people don't understand, like can't understand their language. I mean, what they're doing, and they're being open about it, is talking about how they are evaluating the universe. But I mean, how can you? Because you can't like. I mean, they're saying the exact same thing. Like you can't talk to random people on the street about this, and so they're actually it's like, well, if they're going to these if they're going to CERN and they're going to the Hubble telescope or the new telescope Webb, they're gaining an understanding of that, but they're just not relating it because yeah, it's like there's no reason to relate it. They have um, they're just it's just too much to figure out. I mean, it's too much to figure out regardless. So it's like no, everybody's kind of duping themselves. But to like have the capacity to be honest about this stuff with people, like I mean, especially when you understand just the ramifications of their calculations and their research, and it's never going to look like it's finished or something. And it's like, yeah, I mean, these people are working and everything, and it just becomes, I don't know, very uninteresting to people.
we have our soft vectors. We're going to do a charge expression like that. So let's get to it. Great. So right now I'm just going to write down.
Sorry, what is J?
Oh, J is angular momentum. So that's kind of cool thing. So we have 3 iterations. One of them is the electric charge, which is just this guy with polarization times zero momentum.
And I mean, I guess a reiteration isn't really uh, bad if you're calculating the black hole, or if you're trying to factor out the black hole. Just because, yeah, it's like that's all you can. I mean, that's pretty much all you can gain from the symmetry and the geometry of, or the symmetry of a infrared picture of space. So, I mean, these it's just a little bit confusing to me. Is like when they're taking pictures of black holes in outer space, like um, it's. I mean, I guess it's like theoretically the Hubble telescope or the Webb telescope wouldn't have to travel that far out of the solar system. Well, of course, I mean, of course, it'd be so much trouble if they traveled out of the solar system. So it's like I feel like they are animating. Like I kind of feel like they're animating the black holes, um, but it's like they know that, and they're not. They're just not like. It's not like they're lying. They just have. It's just too much for people to even understand. I mean, and people don't want to pay attention anyway.
And the leading and subleading gravitational soft vectors are going to correspond to super translations and super rotations. And so because they correspond to like the momentum and energies as like the globally conserved charges, and now this is like each particle is probing like that aspect of it. That's where you see that extra soft vector. So like you have this U1 guy here and an extra prefactor of P dot E, basically, and in that case there's a J that comes in. So it's probing that because a different order of Q appearing. But yeah, so great. And it's going to be nice because you can see this with the memory effects. So that's what we're getting to. Over here, we kind of already know what our conventions are, and so I'm going to add the charge for the other two right above charge for. So there's some interest yesterday in the charge for the electromagnetic case. So I'm just write this down.
So the so the magnet, so the magnet would be, they're trying to understand the gravity, so they're trying to understand the magnet that's like holding the galaxy, the Milky Way galaxy together. So it's like they're testing the electricity, the electromagnetism is like, well, the the infrared and the red shift and the blue shift, and then in order to figure out the magnetism, that would be them that would be them studying under the microscope at CERN and like digesting whatever the magnetism is showing them over there. I would imagine. I mean, that's how they have to be able to be able to simulate and animate their their evaluations. Um, so people just don't care to look into it.
And then similarly for the body mass term, we can write down the plus is short of G. Great. So right now, let's just look at those three equations.
Okay, and again, I just want to make sure I'm understanding correctly. Epsilon in the top line and F on the second line are functions on the sphere.
Exactly. So basically what happens here is normally you would have them go to a constant and you would say, oh, this is the electric charge overall. But the point is that now we have this constraint equation here that we're going to look at kind of every angle in some sense. Now, the subtlety is that, so in this case, it's just a function of the sphere, so there's some way we can actually look at this at every angle. Same thing for the bonding mass term once we plug in.
I mean, that's going to be the function. I mean, see, this is why it's money, man, because it's. I mean, they're calling, in my opinion, they're calling a black hole a sphere, and they don't know if it's pushing us out or pulling us in. They just don't know. They don't have enough. The technology isn't great enough to be able to predict that or calculate it or statistically know. So, because you just, I mean, are we upside down? Are we topside up? I mean, that's probably the closest they could get, but they just know that the black hole, I mean, that's what I think that's what she just said. It's like they're just calling it a sphere. They just don't know if it's pushing or pulling.
In the constraint equation, so like you see here, this became integral over u with the partial derivative pulling out from this guy. But in this case, there's some YAs and DAs, so you might worry about like how arbitrary the prefactor is, and so like there's a sense in which only Y holomorphic, otherwise you like, so there's some kernels on that might make that a little bit more subtle. But yes, F is an arbitrary function corresponding to the super translation extra symmetry, and epsilon, the same thing with the large D1. So that's, in a sense, that's why they're kind of similar to each other intuitively. And in the memory effect, I'll show the difference in some sense of like the observable that you would construct from those two cases. Great. Okay. So we have this U1 expression here. What we've done is, let me clarify two things. So when I write these A's, I'm writing out a particular mode in the 1 over R expansion for the actual gauge field. So AU is the 1 over R term in the U component of standard, the A, with the gauge condition that A sub R is set to 0. So
Yeah, I mean, that's going to be like radioactive decay and temperature and all this stuff. I mean, they can say, well, it's acceleration, and the further their particle or the further particles they're able to see, you know, they'll like have an acceleration of what does she call it? Or factor or theorem that is able to predict how hot or cold it's getting, and that would be just by the infrared too. I mean, they could have like just tons and tons of theorems, which I imagine is a formula for a theory. And so, I mean, it's not like they're doing this maliciously, but it's the fact that this stuff is going on, and I mean, it's just this is going on the planet, and then there's like this whole other. It's like there's this whole other world, like this third world thing going on, and I mean, that's a little chaotic to me, but yeah. So memory effects. I mean, memory effects could mean like, well, we don't know if it's entropy or if it's inflation. So, because again, like they both have serious consequences. Entropy theoretically has an ending, and inflation theoretically has no beginning or end. So it's like, and then also like she's talking about harbingers of chaos, and that's talking about the duality of chaos. I mean, they're not going to talk about natural order or get not like be Gnosticistic or Gnosticism. They're not going to be Gnostic. It's not going to be Gnosticism. It's just going to be like really, really tough to just evaluate these things. La-di-dee, la-di-da.
That's choice. Then AZ and AZ bar both are just order 1 fields. The radiated fields are order 1. And then FRU here, it would just be dr of A sub u. And because it's the 1 over r squared component, the electric field, this is the Coulomb field, 1 over r squared. This guy just corresponds to AU here. So that's why we can just plug this expression in, integrate it over squared plus, and then plug into the right-hand side from this guy. So just to know these are stripped of powers of R. And I can write out explicitly. Good. So you do the same thing for the supertranslation case, turn it into DUMB, you can plug this guy in, and yesterday we talked the same thing for the superrotation case using these guys. So use constraint equations to rewrite the charge in terms of radiative modes and like what is leaving no infinity the matter part. Great. Okay. So the other way. This is where.
And the question that is there any issue of is the charge Hamiltonian for something?
So,
is there
so that's the origin of the derivations of the charges. Like,
So yeah, I mean, they're like you just constantly got to be asking questions like, is magnetism doing it, or is like what's going on? I mean, you can't miss a second, or you're not gonna know how they're producing the animation or the simulation or what have you.
like in Varnish, and like you can look at like basically also like this eclectic structure you would expect like the brackets for some brackets for the position space field along null infinity, and also check that the way that we've done this mode expansion gels with that. But yeah, so we basically started from like a lot of work by Varnish to like get to those expressions of the charges that, and there's some issue because normally we have just the variation of the charges well defined, so whether or not you can integrate it to an actual charge. And there's some subtlety also about it being null infinity in the sense that these guys have stuff that fluxes out because you're looking at slices that are null. So there's like
Oh, so yeah, like the slice, she calls it a Cauchy slice, is a Cauchy slice is like her way of saying like the telescope's focus, like what can the telescope actually see. Uh, so, yeah, it's really it's confusing, but it's interesting. So so yeah, I don't know. Now she just seems like she's like a little burnt out, but yeah. I don't know. It's interesting to me. I like this stuff more than the ferrocell. So I'll probably try to make some more videos with her, and if I can, and yeah, I think I'm gonna call it quits. Just because this is a lot, and like I said, I mean, when she was doing those presentations and those slideshows, it's like, yeah, she's using like a way different language, and than when she's like actually teaching a physics class, it seems.